Okay. First, a few important friendly reminders. Code of conduct, harassment and unprofessional conduct is not tolerated. And if anything like that happens, we have ways to report bullying, harassment, or aggression, and the contacts are down here. And then reminders about COVID policies. Thanks a lot for masking inside. And remember to check out the comfort level in everyone's badge when you meet people. Okay. Regarding the virtual participation, so we have in-person people here and speakers, and people are on Blue Jeans. We're going to have most of the presentations in person, but there's going to be one presentation given on Blue Jeans and a couple of recorded ones. So we're going to move through all this. Just a reminder that Rachel here will be monitoring Blue Jeans, and so it's easier to put questions in the chat. The alternative is also to use this Slack channel here for the session. Okay, and with that, our session agenda. So we're going to hear today introduction. We're going to start with Dara Norman on an introduction of the in-kind program. Then we're going to have Maunakea Spectroscopic Explorer by Jen Sobeck, and Software for Making Use of Telescopes Time by William Lindstrom. These are going to be all in-person talks. Then we wanted to give you a few highlights of in-kind contribution teams. So we're going to have Dave Buckley, Jamie Soon talking to us in person here. And then we're going to have a couple of recordings from Taiwan and Italy. And then we're going to shift to different wavelengths. So we're going to have a presentation for the Swift Space Telescope by Jamie Kennea, and this is going to be on Blue Jeans. And finally, radio facilities with Tommy Remijan. And then we hope to have time for open discussion at the end. But after each talk, we're going to leave 2 minutes roughly time, so a couple of questions after that, and then we're going to take the other questions later. Okay, and with that, this is for later. Let me start calling Dara here. And I'll leave it to you. Jen will be giving you the time.
Okay, thank you. Hi, everybody, and thanks for coming. I take it everybody can hear me just fine. Great. Yeah, my name is Dara Norman, and I am the Deputy Director for the Community Science and Data Center at NOIRLab. I want to say first that I was given the title that you see in the agenda, but what I'm really going to talk about are NOIRLab resources for Rubin LSST follow-up. And if you're, I already anticipate I'll be disappointing some of you about information about the in-kinds. And so I want to point you towards this session on Thursday, where you'll get a lot more information than I'm going to give you about the in-kinds. And so I'll proceed. I did want to talk to you about NOIRLab. So NOIRLab really encompasses the NSF's nighttime observing assets in the U.S. And that includes Rubin, Gemini Observatory, the Kitt Peak National Observatory, and Cerro Inter-American Observatory. And each of these assets is clearly an observatory that has telescopes, but there's also the Community Science and Data Center, and our real mission is to think about not just the data and data access for each of the telescopes, but in general for the community and also user support for the community. You probably are already aware, since you're in Rubin, of at least a few of the programs that are part of the Community Science and Data Center, like the Antares broker is part of CSDC. And I'm going to talk mostly about our time allocation committee, because this is the way that we intend to support access to the in-kind contributions for telescope time. There are also, I'm told, some in-kind contributions of external data sets, and those will almost certainly be served in some way through through the Astro Data Lab but I'm not going to talk directly about that today. I really want to tout the fact that we have just modernized our time allocation system. We're really excited about that. And part of the reason for doing that was the anticipation of the in-kind time contribution from different observatories, and now we're equipped to actually handle those contributions. The details of what telescopes you can apply for are available at that website there, and so I'm not going to talk directly about the kinds of instrumentation we have, but you can go to that website and find out about all of the instrumentation and telescopes that you'd have access to through our TAS system. I also, though, wanted to point out that a shout out to our TAC operations team. Even though the TAC is a really important part of what NOIRLab does, it's really only about 4 people who run the whole thing, and a couple more of us who have been at it since the modernization effort. But this is really, they really do a lot. They do a lot of work with just these small number of people. So our TAC process. I want to point out that we already allocate time on more than 10 telescopes, and that number changes a little bit depending on which telescopes we have time contributions from. But we already allocate time on telescopes that are not just things that NOIRLab actually runs itself, but are actually privately operated. So right now we're allocating time, for instance, on AAT in Australia, and also on the LBT, the Large Binocular Telescope. Proposals for most of our telescopes are submitted through the TAS, through that website that I showed you. And that's how we'll be incorporating the in-kind proposals into our review system. A notable exception is the Gemini proposals. Those are actually submitted right now through the Gemini pit, and the Gemini pit is going through an upgrade itself. In the future, we're looking to merge these systems, but right now, each of them have particular functionality that's really useful, and eventually we'll merge them to be one. There are a few procedures and policies I want to tell you about. First, we generally get 400 proposals per semester through our TAS system for, again, those plus 10 telescopes. But they all come into our 8 panels to be reviewed, and the review panels are separated by scientific area. And then what comes out of the review panels is essentially a ranked list of the proposals that should be scheduled on the telescopes that we allocate time for. There are a couple of policies you should be aware of. The dual anonymous review was just incorporated into our system this last semester, and so all of the proposals that come through our system have to be anonymized, and then anonymized in the system, and then of course the reviewers are anonymous to the proposers, which is where the dual comes from. We also allocate on an open skies policy, and that is that anyone can apply for time on our telescopes regardless of their affiliation. This does include, we do get applications from international applicants. They are requested to actually specify why they need to use U.S. served facilities, but we do get international folks using our telescopes already. All right, we currently have many modes and types of proposals available. So again, as we are going to incorporate the in-kinds, we have many ways and many options for doing that. We have a standard standard proposals that are that are served every 6 months. We have a standard proposal call. We also do annual survey proposals. All of the things in purple come through our TAS system. So Gemini actually has a similar type of survey called the Gemini Large and Long programs that are allocated on an annual basis. Gemini also has a mode called fast turnaround that they allocate time on telescopes monthly. And we support both Q and classical types of observing on various telescopes depending on what the telescope asset is. And finally, the Astrophysical Event Observatories Network, AON, is a relatively new mode that we've just incorporated. In the last call, it was officially open for anyone to use. And this particular mode is really geared towards the ability to use multiple telescopes, use them in a dynamical scheduling fashion, or to use Q and Q-like observing for your science. And so just to say a little bit about AON, AON can be thought of in two ways. It's both the actual network of the telescopes, and it's also the collaboration between NOIRLab and Las Cumbres Observatory that is thinking about how we can best serve the science by networking these telescopes together. And so again, the collaboration is actually thinking about these ways to best get science through the network by developing APIs so that you can plug into the network from different telescope assets. They're using SOAR. The SOAR telescope is a Pathfinder for scheduling through AON for on LCO, Las Cumbres. Gemini is actually working on its APIs in order to provide dynamic scheduling and then updating TAC processes. This actually refers to the ability to have observations managed for the observers through TOMS, these target observation managers, to manage when you want to do, how you want to do this dynamic scheduling. And so they're developing those. They've been developing all of this with an eye towards the fact that Rubin in-kinds are coming and will be served through AON. And so I just want to let you know that AON is up and running. It did happen in this last semester and was part of our TAC call as well as Gemini's TAC call. And lastly, I just want to say that currently majority of the in-kinds are expected to serve their time through AON, and that time will be allocated as part of the TAC process. In general, the in-kinds are responsible for serving their own data to the groups, and a lot more detail needs to come about how that's going to happen, including things like archiving, and that will be, that's something that's TBD. So again, if you want to know more about the in-kinds themselves, please come to the meeting or to the session on Thursday. Thank you. Questions?
So there's interest in the community. Might be substantial proposals right in the beginning of follow-up, for example. Given the uncertainty proposal that might be accepted, and then
yeah, so that goes to scheduling, and certainly in the way that things come in, if a proposal comes in, right, that is saying we need and gets ranked highly, and then it turns out that you can't get the the objects that you actually want to observe, that will be a scheduling issue, and we certainly can handle scheduling issues within the framework of how the TAC works that we already have. Yeah.
Following up on Michael's question, it'd actually be useful if
saying, utilize this and try to consider this. That would help a lot.
That sounds good. And Aeon people are here and have heard that. Great. Thank you.
Next speaker is
Hi, everyone. So it's been a while since I've been to a conference, so please let me know. I evidently have a problem speaking up now. I'm just so used to being by myself in a small room. Anyway, I'm here today to talk to you about the Maunakea Spectroscopic Explorer, as well as the MSE Pathfinder project. The whole goal of my talk, hopefully, is to galvanize dedicated spectroscopic follow-up, which I personally believe we are in great need of. So there's a whole host of beautiful facilities that are either online currently or coming online very soon, for instance, LSST. But these facilities really, truly just are going to explore and really just press the domains of science, right? There's just wonderful science to be executed with these guys. However, there's just currently no dedicated spectroscopic facility on a 10-meter class telescope to complement and follow up these surveys. For maximum synergy with these surveys, it's highly desirable that such a facility should start to begin operations, hopefully in the 2020s, perhaps later to the 2020s. So in that vein, I would like to put forward these two projects that we're considering for the Canada, France, Hawaii telescope. Just to remind everybody, this telescope sits on Maunakea. We have two particular projects. The first project, and honestly, this project has been in development for quite some time now, is the MSE Pathfinder. We're hoping, it's MSE, so I'll start with the bottom one. We're hoping for a late 2030s first light. It's going to be follow-up post-LSST survey period, or at least that initial 10-year period. We're thinking it's going to be a roughly 11-meter class or slightly larger primary aperture. It's next generation instrumentation. It is the evolution of the CFHT facility, and it's going to be a dedicated spectroscopic facility. It will not share time with any other instruments. And the goal of MSE is so many things. I really do want to talk to you, and if you want to see me after the session, we can talk to you about the future of astronomy on Hawaii. We've been thinking about this. There have been steps taken since the protest, but I can probably discuss that after the session. But our goal at MSE is to minimize any sort of footprint and extension and really truly respect the culture of Hawaii and the mountain itself. The Pathfinder project is something, actually, it's a little bit of a recent advent, right? We're thinking this is going to be late 2020s, and essentially it's a Pathfinder project. It's hoping to retire some of the technical risk associated with MSE, as well as execute some pretty darn cool science at the same time. It will overlap with the LSST. That is the plan. This is our goal. We're hoping to serve ourselves as a potential follow-up pathway for LSST science. It's a 4-meter diameter primary aperture, so we're not changing the structural facility of CFHT, but we will be changing the instrumentation. And the operations will be extended under the current master lease. So there are no concerns right now, just with regard to the ability of this particular instrument to be built and for the science to be executed. So I just wanted to point out just kind of like what we're trying to do to really truly stay within our footprint and really make sure that we're respecting the mountain and the people of Hawaii. So here's CFHT on the left, and then on the right is MSE. We are really trying to minimize any sort of footprint extension. So even though we're accommodating this huge new 11-meter primary aperture, we are going to try to really keep dome and structural alterations on the order of 10%. So that's our goal right there. And as you can see here, the schematics, and you can see that, with a little bit of fancy engineering, and the engineers can tell you more about that, we're actually going to be able to accommodate not only the actual big optic structure itself, but various instrumentations in the instrument platform. So I'm going to talk first about the conceptual design of MSE, and this is what's been under development for quite some time right now. It's roughly an 11-meter diameter telescope on a 1.5 square degree field of view. There are roughly about 4,300 fibers. There's a low moderate resolution spectrograph. This will be anywhere from about 3,000 to 6,000, potentially a little bit greater resolution. It will go from the UV to the H band, and there are going to be of those 4,300 fibers, 3,200 roughly will be assigned to the LMR instrument. High resolution, we're thinking about instrument will be about roughly a resolution of 30,000. It will have 3 optical wavelength windows, but to be clear, the actual coverage of the instrument is from the UV about out to 900 nanometers, but we will only be able to select 3 windows within that wavelength regime, and roughly on the order of about 1,000 fibers. It is going to be completely dedicated and not share time with any other instruments. The thing is, we've been paying attention. There's been a whole variety of strategic surveys that have occurred, Astro 2020, results from Canada, results from France, results from various communities around the world, and the recent SNOWMAS effort. And we've been thinking about the designs and the conceptual design. So what we've decided to do is actually revisit some of the design and think about how we can increase multiplexing. So we've come up with not only a slight alteration to the conceptual design, but with 2 other really exciting designs, and we're going to have a sort of a review process at the end of the year. But the goal of this is twofold. First, increase multiplexing, like I just mentioned, and second, make sure that we actually increase the wavelength range. So not only will we be able to span from really deep UV all the way hopefully out to K-band. So that's the goal. So we're really looking at this and thinking, how can we serve the community, especially in the future, especially since we'll probably miss some of the most prompt LSST follow-up. So we have a variety of additional technological efforts underway, development-wise. I won't go into these things, but these things are kind of, nice cutting edge and offer flexibility to your facility and your instrumentation. And one of the things that we're considering is pupil slicing. And the other thing we're considering is wavelength splitting. And we're thinking about how indeed this will impact our, how we organize and set up our optics, as well as, how we can kind of compactify matters. The Pathfinder itself is kind of almost an interim type of instrument, right? Unfortunately, it won't be completely dedicated time, but what we're planning on right now is at least quarter time share. We're going to have roughly the same field of view as MSE itself, so a pretty wide field of view. We're thinking around 1,000 fibers. We're going to have a prime focus instrument, so this will mimic MSE itself, but we're also thinking about potentially adding a Cassegrain IFU, and it's something I hope to perhaps speak about with you guys. We do plan to have limited prompt TOO follow-up. So during a night, we're going to have a set number of events that we will indeed, depending on priority, try to follow up. And we will also have dedicated fiber allocation. So a small percentage of fibers in any particular field, in any particular pointing, will be set aside for TVS follow-up. And please note that Pathfinder does not require a new lease. So here's the Pathfinder design, and you can see it will incorporate a lot of the MSE pieces as we've currently envisioned, right? We have an AAO tilting spine fiber positioner. We have a low moderate resolution visible spectrograph. This is developed by Windlight. We have a low moderate resolution near infrared spectrograph, and this is developed by Kral and Lamb. And you can kind of see basically that with prime focus, both of these things will sit on the platform. Now I'm going to shift gears a little bit, and one of the things I wanted to see is how can we best follow up TVS science cases and TVS science needs, right? And there was a fantastic paper by Ngeow, William et al., where they talked about, what are the needs of TVS science. And you can see here that, for transient follow-up, you can, everything is divided into the class of telescope, as well as the types of resolution and wavelength needs that you can have. And so basically in this paper, they talk about characterizing transits, supernova 1A, early supernova, and gravitational wave counterparts. So then I said, has anything actually come out that perhaps is a little more detailed? Because as a spectroscopist, I really want to understand and identify the science use cases. And so just recently, due to the fantastic heroic work of this group, particularly Rachel and Francesca, and I think it's Kelly Hamilton, the editors of this particular roadmap from the TVS group, and I've read through the entire thing, and I just have to say, as a member of SMWLV, this work is absolutely fantastic. But now I think I have a further handle on the exact science cases that really will need spectroscopic follow-up. I think I just need a little bit more detail. But for instance, you can see that for cataclysmic variables, follow-up on 4 to 10 meter class telescopes is preferred, of moderate resolution. And the science that you get out of this is that you're confirming the classifications and you're confirming polar candidates. You are really not just extending the science, but you're making it possible. You're executing it. So I think this is just something that was really interesting, and I wanted to try to develop a little quick look, I guess, table of trying to understand the science cases. And I'm hoping with you guys in the discussion, we can fill in some of this information. So what can you do from a Northern Hemisphere site? I'm not going to get around this. I realize that this is not the Southern Hemisphere site that was called for by in Astro 2020. However, there's a lot of overlap. And so this is a really nice diagram from Melissa Graham. And it talks about basically from Maunakea, what can you actually see of the LSST footprint? And so roughly objects with a declination of -40 and above are visible at an air mass of 2. And so you can see that we're really capturing quite a great deal of the LSST footprint. And right now we think with science requirements and various other things that roughly the overlap is 4,500 square degrees. So specifically, what can we do with MSE? So just thinking about the primary wide, fast, deep fields, right? You have a declination range from -65 to +5. So MSE, with its various limitations, and just thinking about air mass limitations too, because we have science requirements, so forth and so on, we really tried to go for an angle of a zenith angle of less than 50 degrees, right? So roughly anything greater than -30 degrees deck. We're thinking about potentially extending that. And so we're thinking about potentially extending that and making sure that we can actually increase the overlap of the LSST footprint, just trying to be comfortable with the type and the quality of science that we can execute. So here's the idea of potentially following up rapid transits and what we can possibly do, and then comparing that to other facilities. And then I just wanted to go ahead and put up my summary slide right here, but just say that, hey, there are 2 potentially wonderful instruments available at a fantastic site for astronomy. I'm really hoping that we can find a way to work together to organize this spectroscopic follow-up. And so I do have a few questions. So not only are they just little details with regard to wavelength range, resolution settings, these types of things that are needed to execute particular science, but, possibly is there a way to develop a prioritization scheme? I know that these things you guys have been thinking about already, but I'm hoping perhaps we can start to get that in the works. What are your sample follow-up sizes? Are there ways to actually bootstrap from a calibration sample or some sort of set gold star sample to further science in a particular, for a particular science case? What about high resolution? When I was looking through the TVS science case, I only saw one call and one need for high resolution. So perhaps your community doesn't need that. And then what about IFUs? So thank you very much for listening. I appreciate it. And just talking with the Remijan employees, if you guys don't mind, one thing I also thought about is, will spectroscopic information be used to inform Remijan observations? If so, this path gets easier for us.
I'd like to raise a question that came in on the Slack channel from Ms. Alyssa Brucker. She asks, will there be an imaging replacement for CFHT's capabilities? Also, there may be planetary defense asteroid science cases for the Pathfinder.
Oh, absolutely. I have not mentioned probably like a quarter of the science cases that we can think of for MSE. With regard to imaging, MSE was always intended to be spectroscopic. And I have to admit, I'm biased. I'm a spectroscopic person myself. However, we've been talking about it because with different mounting schemes, the possibility of instrument exchange is there. And I'll be practical. We need to fund this instrument. So if indeed imaging brings to us something that's different and we can harness the capability of the Maunakea site, we're going to consider it.
Thank you.
What's the field of view of the Pathfinder?
Both are going to be around 1.5 square degrees, but Pathfinder will probably be a little bit less. It just depends if we can buy a corrector optic.
Okay. Hi, I'm William Lindstrom. I go by Lindy Lindstrom from Las Cumbres Observatory, and I'm a software engineer there. And so yeah, I'd like to talk to you about some software tools and services that are there for you to support your follow-up observations in the Remijan era. And they fall broadly into 3 categories. Each one of these is pretty big. So my goal is just to introduce you and point you to further resources in each one of these categories. And they kind of go from big to more local in scale. So so starting with AON, we had a great, thank you, introduction to AON. So I can focus on what it is, the collaboration between observatories to facilitate time domain follow-up astronomy. And I'll present sort of more technical information where what we're really, AON it's Gemini, SOAR, and the Las Cumbres observatories right now initially, but we are encouraging more participation. So that would be great. So what would it take for you to participate in AON? And there's really only two requirements, and they're technical. They're not anything other than that. And one is that your observatory be queue schedulable, and the second requirement is that it's programmably accessible, meaning your observation requests are coming in via the web, via an API or something like that. So, and we'll see how both of these requirements are supporting the time domain follow-up. And so dynamic scheduling, this facilitates target of opportunity observations and long-term monitoring over fixed windows. If you want to support a cadence where you're observing your target every 2 weeks over a period of time, queue scheduling is going to facilitate that. I don't need to go too far into that. And then the second requirement, is that your observation requests can come in through an API. So if you're observing on a cadence, you're not going to be traveling to the mountain every time. So this facilitates you making your observations requests from your office. So that is it with respect to the requirements to participate in AON. And I would stress that each one of these observatories is participating in its own way, and in a way that is appropriate to them. So, so for example, SOAR is not robotic, but they're using the LCO scheduler. And Gemini has implemented its own API, and we'll see later how Tom Toolkit will facilitate submitting requests to that, and does facilitate submitting requests to that API. So these bullet points. So common standards, and again, I would, it's designed to be easy and inexpensive to participate. So you can use our software, you can use your own software. You don't have to be robotic, and all the time allocation is in the control of the observatory. Further information, so here we've given a couple of SPIE talks about AON, and then the websites for each of the participating observatories. Your observatory could be one of these, are here. So then, so the capabilities, queue scheduling and programmatic observation requests facilitate time domain follow-up observations, whether you're participating in AON or not. And so next we get onto some tools that might help you at your observatory implement those capabilities. So the open source observatory control system. This is a project that I'll go into from LCO. Basically, it's our control system that we've developed over the years and is in daily use. We've basically open sourced everything. We've removed all the LCO specific parts of it, and are now making it available for observatories who want to go this direction, but maybe don't have the software development resources to start from scratch. they can use this. So yeah, let me take you through some of the applications that comprise the entire observatory control system. And I will start with the observation portal, because this is kind of the central, it's what the users will interact with. You can manage user accounts, proposals from, and make observation requests and get statuses of observations and the data from those observations through the observation portal. And so that's really your user-facing component of the system. And if you've used LCO, you've used our observation portal, and that's what's available to the community. The other, I want to touch then on the configuration database, ConfigDB, because it's the other core component. And this component basically just functionally, it's the database that describes the state of your system. Your instruments, whether they're schedulable, whether they're in commissioning mode, whatever, that information is in ConfigDB. It makes its information, when the scheduler is actually scheduling the observations from the observation portal, it's referring to ConfigDB to know, well, can I schedule this observation on that telescope or that instrument? So that's ConfigDB. Quickly, OpenSearch is our telemetry database. It was Elasticsearch that we've then upgraded to, or migrated to OpenSearch. I'll just quickly touch on the downtime database is that came about with Aeon. So the downtime database is where we store the information, like SOAR is available on these nights of the semester, and on the nights where SOAR isn't available, it's in the downtime database as unavailable. And the scheduler uses that information. So the scheduler itself, okay, so this is, it's our kind of pride and joy. It's a nice, so it optimizes observation requests over the entire network. And it's continuously running. It'll generate a new schedule every 7 to 10 minutes. So if there's bad weather, Cape Town, those observation requests will be rescheduled for Tenerife, for example. And so that's available, but again, it's not an essential part of the system. And then finally, the science archive is where science images go, and that's where they're, 2 minutes. So more information about the OCS is, it's all open source. It's our website is on GitHub, and I would refer you to that. And also John Nation's recent last month SPIE talk, if it's available to you, is a good resource for that. Okay, so then finally, for astronomers running programs, we have there are target observation managers, TOMs, and and there's several or a couple of software packages to help you with that. So TOM Toolkit is what I'm involved in and most familiar with, but a Sky Portal is also there. And I sort of in my mind can distinguish between TOM Toolkit based TOMs and other TOMs. But basically, the TOMs have interfaces to data coming in via brokers, via catalogs, via alerts systems, and then centrally manage a database of targets, a database of observations and data products, and references into the data archive. And then in order to actually get those observations and data products, there are interfaces to facilities. So we have an interface to SOAR and Gemini and Liverpool telescope, for example. So you, as a telescope operator, you can, one method of participating in Aeon is to implement a facility module for TOM Toolkit, and then TOM Toolkit-based TOM users could submit requests to your facility. So here is an example of, the type of interface that we're presenting to astronomers and people running programs This is the Supernova Exchange 2. The SNEX Supernova Exchange originally was not a TOM toolkit-based TOM, but it is migrated over. Yeah, and so see data products. We don't see observations being requested here, but yeah. So, and here we have a little bit more about the I/O. So interfaces to broker surfaces are there, and that will expand for all the community brokers. And then interfaces to observing facilities, and then centrally, this is where you run your program from. This is Django based, so Python developers should be comfortable with it. It's the Django is the Python web framework, and so from that we can get user accounts and permissions. That just comes with the Django framework. Yeah, in summary, this really is an ecosystem. These systems are designed to work together. Yeah, and I think that hopefully was clear in the talk, and yeah, ready for.
We have one question from Slack from Dragana Illich. Question for Lindy. Will Aeon operate with some specific TOMs, e.g. like the TOM toolkit?
Yeah, yes, that, right, yeah. If you've met the requirements to participate in Aeon, TOM toolkit can implement a facility module for your facility. So yes.
And then we're going to have our series of highlights now on in-kind contribution. So our first speaker here is David Buckley, and leave it to you. Thanks a lot.
Great, thanks. Yeah, sure. So I'm going to talk to you about the one component of the South African in-kind contribution to LSST, which is optical follow-up facilities. And I'm going to break it down into two parts, into SALT, the Southern African Large Telescope, a 10-meter class telescope, and then everything else, which is the other telescopes that we host at our Sutherland observing site. So this is just a sort of encapsulation of the key aspects of this telescope. It's a rather unusual design, which I don't have time to go into, but it's a telescope with a changing effective collecting area. At the worst, it's equivalent to a 7-meter. At the best, it's equivalent to an 8.3 meter. The current instrumentation covers basically the UV cutoff of the atmosphere to 900 nanometers for a number of different instruments. And then just this last few months, we've been commissioning a near-infrared spectrograph, which should be fully available to the community in 2023. So the instrument listed there. I'm not going to have time to talk about the details. Suffice to say that the Robert Stobie spectrograph, which is the workhorse instrument, is the one that we've been using extensively for time domain astronomy and transient follow-up within a program that we started back in 2018 of transient follow-ups of many different classes of objects. So it has a variety of capabilities from low to medium resolution spectroscopy, multi-object, long slit, Fabry-Perot imaging spectroscopy, fast imaging spectroscopy, and polarimetric modes. And the other instruments are a high-resolution spectrograph, fiber-fed instrument. Here's some pictures of the three instruments that we currently have. The one on the left is the prime focus instrument. It's hovering in the air there as it's being put back onto the prime focus after some engineering work. The high-resolution spectrograph's on the right. It's a HARPS-like vacuum-stabilized, temperature-stabilized, fiber-fed spectrograph, which will be shortly implementing a laser frequency comb for people who are interested in precision velocities. And then Salticam is just the imaging camera, but it's a fast imaging camera. So the instruments all support high time resolution, no dead time observations. So we can do spectroscopy at 10 hertz if the signal to noise is good enough, and we have. This is the new instrument that I was talking about that's coming. There actually. So this was an instrument built by one of our partners at the University of Madison, and it's a fiber-fed IFU going out to 1.7 microns. And then from about 2024, we're hoping to implement a new arm of the existing spectrograph RSS, which will extend or give us the capability of doing a wider simultaneous wavelength coverage with this new red spectrograph or red arm, which will be a lot more efficient than what we have at the moment. In terms of access, we're basically giving 50 hours a year for this program, this in-kind contribution program. And I won't go into the details of how this is going to be done for the LSST US and Chilean community, but basically it will implement or use the existing proposal systems that we have, with the addition, of course, that NOIRLabs will have their own TAC that will assess the phase 1 proposals initially, but from there on it'll go through our system, and we're hoping actually in the next month or so to beta test the first SALT API, which will allow things to be more automated in terms of populating the observing queue. The data is always available, typically the afternoon after the observations were taken, in some form of pipelined data reduction. So it's a fast turnaround system, which is actually ideal for the sort of science that TVS and I would say other science collaborations within LST would like to exploit. This is just a SALT proposal flowchart, and you can see in red there the hooks that will come in with the APIs to allow for automated addition of objects into the queue, and of course they will interact themselves with TOMS and so on. So it'll be a fully AON compatible system. I'm now going to move on to the other telescopes, and my colleague Steve Potter is responsible for this provision of in-kind, but basically we have a number of 2 to 1 meter, even less, telescopes on the summit, covering a wide range of capabilities, some wide field facilities, and a couple of them I think may be quite of interest to the community. That little photo just shows the 20-odd telescopes that we have there. They're not all South African. Many of them are hosted facilities, but we have access to those facilities, and I'll talk about what we have, what we own ourselves. 3 telescopes, 1.9 and 2 1-meter telescopes. The most recent one, Lesedi as it's called, is a 1-meter Altaz telescope with some quite nice novel instruments in the Naismith focus, and that has now been fully roboticized. So we've actually started just in the last month to be able to programmatically follow up on alerts, which we've been doing very successfully. As far as the SAO hosted facilities are concerned, this is the most recent one that was installed last month, and we got first light just towards the end of July. This is a wide field infrared telescope, which is provided by the University of Osaka, and also NASA, University of Maryland, are providing the camera. This is a 1.5 degree field of view going out to the H-band. And although its primary purpose is not necessarily related to LSST science, it will have a role in transient follow-up and targets of opportunity. And then another facility which is hosted by us, which is owned by the University of Göttingen, is Monet South. It's a fully robotic 1.2 meter telescope, and this is probably another example of a successful morphing or sort of upgrading of the operations system using exactly the systems that were spoken about in the previous talk, namely the LCO OCS system. And so we're currently working on a project in South Africa that started in 2020 to what we call develop an intelligent observatory, to link all of these telescopes together into an autonomous machine that is able to take alert data and decide without human intervention what's the most appropriate telescope and instrument to use for follow-up. So I think this will be something of interest to the community here who want to exploit these follow-up facilities. And we've already started with, already had great success in converting our ancient telescopes to remote control, and more recently to fully automated control programmatically. So I'll end there just with this slide, which, as far as those facilities are concerned, we have the agreement of providing 52 hours of time per year on those facilities. And I'd be quite happy to speak to anyone about what you think about what I've just spoken about. And I just unashamedly advertise the Unconference movie time, which will show what I think is quite a cool video talking about the Intelligent Observatory, particularly in context of our follow-up of GW 170817. So please come along and see that later this afternoon. Thanks.
Okay, our next speaker is Jamie Soon, and I'll leave it to you, and we'll wave.
All right, thanks. I'm Jamie. I'm a final year PhD student at the Australian National University, and I'm here to talk to you about DREAMS, the Dynamic Red All Sky Monitoring Survey, just to start off with. So DREAMS will be, I guess, sort of similar to Rubin, as in searching for transient and variable stars. We're using a 0.5 meter near-infrared all-sky survey telescope, and that's located in Australia. The original design case for DREAMS was to be built to search for electromagnetic counterparts to gravitational waves. There are many benefits for this. Happy to talk about that in other cases. However, I would also like to point out that it isn't, and even though we're in the in-kind sort of section, it's not part of Australia's in-kind contribution to Rubin, but there are many benefits in tying the DREAMS survey, I guess, to Rubin, which I'll come to shortly. So context first, I guess. So we're all aware that Rubin is down there in Chile and Australia is over here. So that's fairly good for a lot of reasons, but a lot of it is that as objects are setting in Chile, they're rising in Australia. So very quick follow-up there. But there's also, I guess, a certain overlap during winter where it's possible for us to have, I guess, contemporary observations for a few hours, 2 or 3 hours, possibly. I guess just for some more context as well, SSO is located where the telescope picture is, and I guess Sydney's over there because most people know where Sydney is. So how are we doing this? So normally if you've used any kind of infrared instrument, these normally use what are called Mercatel detectors, mercury cadmium telluride. So they basically do all the JWST stuff as well. But because we're a sort of smaller instrument and we wanted to go sort of on sky much quicker, we're using these InGaAs detectors. So they're indium gallium arsenide. So they're not normally used for astronomy, but there are a couple telescopes sort of coming online that are using them now. The interesting part of these detectors is that they do have a shorter cutoff wavelength region. So in the sort of dark red color that you can see at the back, that's the responsivity of the detector. And the 3 filter profiles I show are just the design requirements that DREAMS was designed for, as well as your just normal filters. It does mean that instead of having a traditional H filter, we'll have a H short filter instead. So just onto DREAMS itself. So that is what DREAMS will look like. 0.5 meter. So in terms of length, it's basically as tall as me. It's a 0.5 meter telescope, which I did mention earlier. Yep. And this is basically the inside bits of it. I'm also happy to talk about this afterwards if you're interested. And I did also bring a poster along that sort of shows the more optomechanical parts if you're interested. But I guess more to the relevant bit for this section, is this, well, sort of. So we're planning to go on Sky towards the end of this year. Currently the date is around October. So we have all the majority of the parts in-house and we are hoping this year. So for this slide, the interesting bit is, I guess, the left image there. Laser pointer. So for various optomechanical reasons, what we're doing is sub-selecting, I guess, fields in the telescope field of view. So that's determined by these 6 field lenses here. And then more interesting bit is this. So here we go. So these are the 6 sub-selected pics with our telescope field of view, which was about 12 square degrees, but because of our detector field of view in total ends up being around 3.71 square degrees. So because of the, as I mentioned before, the optomechanical design, we do end up with large detector gaps. So the way we're sort of filling in these gaps is with this preliminary tiling pattern. So this is just 4 pointings to fill in the gaps, and this is the moon, because everything like this needs a moon. So we will end up with, I guess, areas on the sky as well, where you end up with either areas of deeper coverage or higher cadence, depending on how you want to look at it. And the more interesting bit for Rubin is this bit. So in this image here, I've just shown the field of view of Rubin and then the field of view of Dreams. So it's a very similar sort of overlap. And I didn't mention it yet, but I'll mention it now, so the design survey of Dreams is supposed to be down to the 17.8 magnitudes in the J band every 4 to 7 days. So that sort of also lines up with Rubin as well. So there is a lot of, I guess, synergies between them. So it would be actually really helpful as well if Rubin provided their pointings as well as filter configurations in real time. So as it is a survey telescope and not an in-kind, we're not offering telescope time or the Rubin community, but we do have the potential, well, as I mentioned, to shadow the Rubin pointings, as well as we do support TOO requests for other various purposes. We're not sure at this time whether or not we will be offering all our data, I guess, publicly, like the same way Rubin is, at least for the alert level. So in my current thinking, we will have like an initial period of, I guess, a few years of private data based on people who've contributed to the project, etc. So this is my last slide here. Hopefully I've covered it all. So it's a 0.5 meter telescope in the near infrared, so with the YJH imager. We're hoping to go on Sky at the end of this year. I also should have mentioned that the pixel scale is around 2.48 arc seconds per pixel, and it's not in-kind facility. So this is just a timeline which might be a bit hard to read down the bottom. So Dreams we're hoping for roughly a 5-year timescale. So this will overlap with Rubin significantly. Of course, we would like to extend it longer, but that's funding related, of course. And a nice little overlap with the Roman Space Telescope, and of course with the LVK Observing 1, which it was originally designed for. Thank you.
Michael Strauss, I wonder if you can say a little bit more about sort of what the observing plan is. Is the idea, you said to go to 17.8 every 4 to 7 nights, but do we think of that as the default observing cadence or what?
Yeah, so you think of that as the default observing cadence, though a lot of that is still in, I guess, flux. Like similar to Rubin, we won't know exactly what will come out until we go on Sky. So hopefully by the end of this year, we'll know a bit better. So that's the initial preliminary all-sky survey. We are thinking of doing targeted surveys primarily in the plane, but there may be other fields which I guess are more useful as well. These may include the deep drilling fields that Rubin's doing, but a lot of this is still to be determined, which is why I'm here as well.
Tim Jeunesse comments from the Slack channel that they will be reporting telescope positions along with the upcoming schedule to enable this kind of shadow survey.
Yeah. Do you know, did he mention if they'll be reporting the filters as well?
He doesn't mention that, but I'll post it on Slack and hopefully you'll get an answer that way.
Oh, hopefully is the answer. Thank you.
Okay, our next couple of talks are recorded, so bear with me when while I try to do some technical magic. Or retry to do that. Okay, this is the Taiwan contribution, so I'm gonna play that.
Hi, my name is Ngeow, and I am from National Central University in Taiwan. The in-kind contributions we provided to the Rubin Observatory is a new 2-meter telescope. We tentatively call it Trans-Pacific 2-meter telescope. So this 2-meter telescope will be located at San Pedro Mateo in Mexico.
Okay, let's try that again.
Through the way? Yeah, exactly. Of course.
I hope it's okay for the people in blue jeans down.
Yeah. Oh no, that's perfect. I'm sorry.
Yeah. Yeah, so people in blue jeans, let us know how this works. Might be a little loud.
My name is Ngeow, and I am from National Central University in Taiwan. The in-kind contributions we provided to the Rubin Observatory is a new 2-meter telescope.
You want me to do the PDF? Yeah. Sorry, folks, that isn't working properly. So we're gonna attempt to show you some slides. Sorry, what? Oh. Okay. I'll let Jen do that. So why are you saying it won't work on blue jeans? Okay. Okay.
Hi, everybody. I don't know what I'm talking about, but I'm going to try this. So hopefully I represent our Taiwanese group members and collaborators well. So this is an overview of a Trans-Pacific 2-meter telescope. It's a new and novel effort. And it's going to be a 2-meter aperture, as the name indicates. The wavelength range is going to be optical to the near IR. It's a 4-band simultaneous imager at first light, JHK imager, and low R spectrograph or IFU to be added. So there's going to be 2nd-generation capability. This is quite exciting. This site is actually under construction in Mexico. So it's a North American-based facility, which, of course, there is convenience implied in that, and expected to be completed in 2024 with 4 institutional partnerships across the Pacific. So here's kind of just like basically a schema of, the institutional partners, so forth and so on. And then just kind of thinking about, not only the setup of who or the players are in this particular instrument generation, but then thinking, of course, with reference to the Vera Rubin Observatory. Hope that was the point. The telescope itself is a Remijan design. The effective aperture is about 2,000 millimeters, so it's quite nice, the effective aperture. Focal ratio, primary f2 with a combined f8, and it's all as-mounted telescope with a slew rate of 4 degrees per second, so that's not bad. There are 3 instrumentation mount points, Cassegrain, and 2 Naismith platforms. The seeing is anticipated to be around 0.7 arc seconds. Photometric nights around on the order of 70%, and spectroscopic nights on the order of 80%. And here I think it's just a photo of the site as well as a schematic of the actual telescope itself. This is quite nice because it reminds me of APO. I don't know how many of you guys have been out there, Apache Point Observatory, but it's definitely bringing back some fond memories for me. But yeah, that's the particular site. And it's nice to see another site where trees actually can get in your way. Quick story, we had to cut some down just to see the bulge at APO. Anyway, so now let's talk about the real meat and potatoes and the important matters of this talk, with regard to LSST, so those pertinent facts. The telescope time available is expected to be on the order of 40 nights per year for 10 years. This is all made available to the Rubin community. There's going to be, an application process, of course, for the telescope time. There's basically through NOIRLab TAC process, as described by Dara earlier, and addressed in a session later on tomorrow. The observation scheduling is going to be time allocation based on what the NOIRLab TAC process actually delivers. Planning for fully Q operations and Aeon compatible, yes, type of scheduling. Plan for flexible scheduling with multiple programs per night. And I'm wondering if we could potentially ask follow-up about TOO. Accessing the data products. This is something quite important because we've all, kind of been told that with in-kind programs, they will have to serve some of these things. Data pipelines and archive are under preparation. Expected data products are calibrated images and associated catalogs. So they are going to make these available to our Rubin community. And I think that's it. Can I try, Maria's? The work?
This is less of a question, more of a comment.
Yeah.
Which is that San Pedro Martir had been one of the initial sites considered for Rubin itself.
Oh, really?
And it came down to San Pedro Martir versus its current location, Cerro Patron. It was quite close. I've been to the summit there. It is the darkest site I have ever been to. It is an amazing site.
Oh, that's fantastic.
I'll just comment there.
I can't wait to go down there, hopefully. There are comments. We'll take them. Yeah. Is there anything from the chat? Nope. Okay.
It's something else.
Okay. You want to try Maria's and see if that works better?
Yeah, we'll try.
Okay, cool.
So we have another recording. We'll see how that goes. I think it's this one.
From Italian.
You can?
And I will. From Italian National Institute. Thanks everyone. I am Maria Teresa Botticella.
I think you have
from Italian National Institute for Astrophysics, INAF. And I will briefly present the optical facilities which our community proposed as in-kind contribution.
Okay, we're going to be very grateful to Jen here.
Maria Teresa Botticella.
Sorry,
from Italian National Institute.
What I'll try to do,
there we go.
Okay, so this is brought to you by our Italian in-kind collaborators through the in-kind program. This is written on behalf of Maria Teresa Botticella, and she's with INAF. So this is an effort called from VST at Cerro Paranal. This is a telescope that has a 2.6 meter primary aperture, a wavelength range of 350 to 1,000 nanometers. The instrument suite includes a wide field imager called MegaCam. It's 16K by 16K pixels. It has 12 different broadband filters and 2 narrowband filters designed around the H alpha emission line. That's quite nice. The field of view is roughly about 1 square degree, so kind of a wide field-ish. The pixel scale is about 2.1 arcseconds per pixel, and the optical design is an f5.5 modified Ritchie-Christian reflector. And there are adaptive optics available for various, corrective. So the telescope time available, it's still to be discussed. I think all in-kind programs are working through this. It's kind of a novel type of effort. So they would like to support the commissioning operations of the Rubin telescope. So there are 120 nights in the years 2023 through 2025 to provide independent data for cross-calibration of the first Rubin images. There will be follow-up observations on the order of 35 nights per year made available to both the U.S. and Chilean communities for follow-up observation of LSST targets or other types of scientific investigations. The support of the LSST survey during operations is also planned. So 65 nights per year used to execute surveys that may be complementary to LSST science in terms of temporal baseline coverage as well as photometric depth and completeness. And they're currently envisioning 3 different types of surveys right now. A precursor monitoring survey on the DDFs or other specific fields as proposed by the science collaborations to extend the duration of LSST AGN light curves, thus improving the detection and characterization of transient variable sources and providing template images at the beginning of LSST operations. That's cool. A high cadence daily monitoring campaign of roughly about 30 galaxies and about 10 cluster lenses in 10 years. This data will allow for the measurement of light curves and time delays to roughly on the order of 2% and to build high quality weak lensing mass maps. And then finally, a co-survey within the LSST footprint to fill temporal and or filter gaps, providing ancillary data to maximize the effectiveness of the main survey. So the observation scheduling, as expected, is TBD. But right now it seems to be just kind of what was discussed, but now these are the exact details. So 2023 is 50 nights for Rubin commissioning. 2024 is 50 nights for Rubin commissioning plus 15 nights for follow-up. 2025, 20 nights for Rubin commissioning plus 15 nights for follow-up. And then from the 2026 to 2036 period, 65 nights per survey per year for the survey plus 35 nights for follow-up. The data product access is also TBD, but they're going to perform data reductions at the VST data center based at INAF. And so they've been doing this process for quite some time, have some experience, and they'll try to make the data products available through there. We aim at releasing to the LSST US and Chilean community, the co-added and calibrated VST images for selected sky fields, the catalogs and light curves for all transients discovered in these fields. Our contributed data set will be accessible to all as LST members in a timely manner by the start of Rubin operations. There are other Italian facilities available for follow-up. The LBT, which is on Mount Graham in Arizona. The LBT is a 2 by 8.4 meter telescope designed to deliver AO corrected observations equipped with 3 instruments. The imaging camera, which is a 23 arc minute by 23 arc minute prime focus camera with a blue enhanced and red channel. The optical IR spectrograph mods covering the entire wavelength range from 3200 to 10,000 angstroms. And the ZJHK near IR spectrograph Lucci that INAF will offer 2 nights per year for Rubin commissioning and 20 hours per year for follow-up, both spectroscopy and imaging. SOX, which is at La Silla. It's the son of X-Shooter. It's a medium resolution, roughly around 4,500 resolution spectrograph, wide band with coverage from 3,500 to 2,000 nanometers, and it's mounted at the 3.6 meter NTT. INAF will deliver 2,000 spectra obtained with SOX from LSST targets. Observations and data reduction will be executed with the guaranteed time observations secured by the SOX consortium. The targets will be observed over 5 years at a rate of approximately 400 per year. The deliverables include the entire data acquired for these targets, which will be one-dimensional extracted spectra and spectral classification. And that's about it. So, thank you. And yeah, questions. And so, like I said, we can post these questions to the various investigators and then follow up in the notes with responses. There's Jamie's talk next.
Okay, so Jamie is up next, and he'll present. Yes, he'll present via BlueJean. So Jimmy, we'll want to have you share screen. Perfect, we see it. And then I'm going to mute the audio here so you can test the...
Okay, you guys hear me, right? Let me see if I can... you guys still see the slides?
Yeah, works great.
Great. Okay. Yeah, so my name's Jamie Kennea. I'm the Science Operations Team Lead and also the X-ray Telescopes Team Lead for the NASA's Neil Gehrels Swift Observatory, which I'm going to show you as a TOO machine. This is a nice Lego model of the Swift. It consists of 3 instruments. The Burst Alert Telescope, which is a hard X-ray telescope which covers about 1/6 of the sky. Detects about at design it detected 100 GRBs a year, a few less than that now. We have an X-ray telescope which has a smaller field of view, so 24 arc-minute diameter, very similar in design to the XMM Epic MOS telescopes, but a lot less collecting area. But we can get good sensitivity imaging with and positions as good as 1.7 arc seconds. And finally, we have the UV optical telescope, which is a Richard Chrétien telescope with a 17 arc-minute field of view, and it has 6 filters, 3 optical, 3 UV, 2 grisms, 1 optical, 1 UV, and it also has a broadband white filter, which is essentially no filter at all. And it gets down to about 20-second magnitude in the white filter in a kilosecond of observations. So what makes Swift unique? Well, obviously it's a multi-wavelength platform. A lot of these things are space unique. So the hard X-ray, and UV can only be done from space. We have rapid slewing. You want to get to a GRB fast, but it also means we have very high efficiency operations. 75% of the time we're observing, the rest of the time we're slewing and going through the SAA. This means that time domain astrophysics is something we can do because we can perform high cadence, high sensitivity monitoring with low overhead. We did have a broken reaction wheel earlier this year. We had 6 and 1 broke, but even with 1 broken, we're still pretty fast. 6 is a lot for a spacecraft. We have a TOO capability, which means that we can actually repoint Swift on the fly just by sending it a command. So that means that we can respond to TOOs within minutes to hours. We're constantly evolving our ground and onboard software, so we don't stand still. We're working on automation. We're trying to get faster and faster, despite the fact we have a very small team. And our team is very motivated and agile. We have an open and broad TOO program. We have a low rejection rates for TOOs, and our data is made public ASAP. There's no proprietary period. And it's a GRB mission, which is important because interruptions are expected. So unlike guys like Hubble and JWST, if somebody's observation gets interrupted, that's just as expected. So that means that we can be very flexible. So what are Swift's TOO and observing capabilities? Well, Swift's in low Earth orbit, which means there's a 96-minute time to get around the Earth. And in a 96-minute orbit, we can typically observe for 42 minutes of that. But we're limited to 30 minutes per orbit. We can slew rapidly within minutes to any target. We can't observe during passages through the SAA. The speed of observation is limited of our ability to make contact with Swift. So typical method is using ground station passes, which means if somebody puts in a TOO for one observation ASAP, we may have to wait for a ground station. Which can take like an hour or sometimes longer. We also have the ability to command through TDRSO, which gives us a 14-minute latency. And a typical observing strategy for Swift, observations are like most you want to ask for is between 1 and 5 kiloseconds. Anything over 1.8 kiloseconds will have to be spread out over several orbits, so it'll be broken up into chunks. Longer TOOs are possible, but remember, we get a lot of TOOs and there's only so many seconds in a day. So how many TOOs do we get? Well, in 2021, we received 1,742 TOOs in just in the year, which is about 4 per day. We approved about 99% of those, slightly more than that. But we do perform them on a best effort basis, and which means every TOO we retrieve is assigned a figure of merit, and the higher that merit is, the more likely it is to be observed. So if you want your Swift TOO to be observed, the best way to do that is to juice the figure of merit. And the best way to do that is to apply for a TOO program through the Swift GI program. And the Swift GI program, I'll note, is the proposals for the next cycle are due next month, September 25th, I believe. So time to start thinking about those if you want to get observations between April next year for a year. Also, observations coordinated with other observatories receive a higher merit as well. So we've seen this rapid rise in TOOs over the time, and what's causing that? Well, part of the thing is the number of optical surveys that exist. They're just making a huge discovery engine for transients. And of course, with Assassin and PTF followed up by ZTF, we've been seeing now a rise in optical transient discovery, which has led to about 1/3 of the TOOs coming into SWIFT coming from optical surveys. So of course the future is the Vera-Rubin Observatory, and we expect that to be very much driving our number of TOOs in the future. So how do you go about submitting a TOO? Well, here's the old method. We have a TOO web page, and it's pretty simple. You just fill out the requests and instruments, coordinates, and how long you want to observe for, and instrument configurations. Probably of most important is understanding how the urgencies work. If you want observation within 4 hours, we have urgency 1, but that's only for the most exciting events because that wakes people up. We have urgency 2, 24 hours. Most of the people putting in TOOs for like supernova use that because they want to get like early data. And then you get the sort of days to a week to months TOOs. I'm expecting most transient TOOs will be urgency 1 or 2. So, but only use that for the first observation, not for extending observations. All right, so that's the old way. The new way is we have an API. Everyone's talking about APIs, and we have one too. So Swift TOO API allows direct TOO submissions in a simple and defined format, which is a JSON format, without the need to fill out the Swift form. So Swift TOO web form. So that means you can automatically submit TOOs without a human in the loop. We have server-side processing of the TOO, which allows filtering on specific criteria. So you can imagine a situation where we could plug into a transient broker and auto-generate TOOs for targets that meet specified criteria. The criteria obviously would need to be set so that you get a sensible rate of TOO requests. You can't be sending us like 1,000 TOO requests a minute. So, if you want to use this, then the group should coordinate on this to limit rates. So if you come up with a script that produces 1 TOO per day, that's fine for us. But, if there's 100 of those scripts running, that could become a real problem. API clients can be implemented in any language or for any platform. For example, the Swift TOO webpage I showed you on the last slide is actually a TOO API client implemented in PHP. The API also provides an interface for a variety of TOO planning activities, allowing you to do things like calculate target visibility to Swift, search for prior and upcoming observations, and look at previously submitted TOOs and much more. So this is the reference implementation of the TOO API, and it's in Python because everyone uses Python. And on this slide, I've just put some instructions as to how you can get started with this. So it's a module called Swift Tools, and there's a submodule called Swift TOO. You just install it using pip. On this website, there's a link to the instructions, and more importantly and more usefully, there's a whole bunch of Jupyter Notebook for download on that website, where you can learn how to use this API. And you can see an example of the Jupyter Notebook on the right shows you how to submit a TOO using this API. So Swift and Rubin, well, Swift is ready to support Rubin with TOO follow-up. Obviously, our ability to cover X-ray and UV wavelengths is unique, certainly in terms of the number of TOO follow-ups we can do and how rapidly we can get on target. Swift does currently handle a very large number of TOOs, but with some developments, I think we can do more. There's some automation efforts underway at Swift right now to try to be able to do more observations of TOOs without human in the loop. And really, the only limitations on our ability to do these TOOs is the human, whether, how much a human can do, and we're a very, very small team, but also how many seconds there are in the day. But equally, I think we can do a lot more. So we encourage you to apply for the Swift GI program, as I said. And yeah, remember, there's only so many seconds in the day, and Rubin could easily overwhelm Swift, but we want to do our part here. So final slide, just to sum things up. We're a multi-wavelength instrument, rapid slewing, flexible software. We've evolved from a GRB mission into a TDAM mission. We're really popular for doing TOOs, 4 to 5 TOOs a day, and we're capable of rapid follow-up in minutes to hours. So this presumably, the number of TOOs can be driven up by the increase in large-scale optical surveys, and Rubin will take this to the next level, I think. So we developed this TOO API to try to handle this by moving TOOs into a computer-to-computer interaction. And Swift's ready to support Ruben. However, I think we need to work together with teams just to make sure that the TOO request rates are reasonable. So that means probably a few per day, so the Swift team's not overwhelmed. Thank you. And I'll take any questions.
Thank you, Jamie. Any quick question? Is there any from the chat? Okay, if not, thanks again, Jamie, and we'll switch back.
All right, thanks a lot.
Thank you. Our next speaker is Tommy Remijan, and he's gonna be giving us an overview about NRO radio capabilities. And if I can find the, oops, Tony, I'll leave it to you before I mess up your slides. Sorry.
Okay, thank you very much. Thank you for the introduction, and really gave us NRO a kind of kick in the pants and start thinking about this over the last several weeks. Also, Jen, do you want to do it or not? No, okay. All right, let's go. The goal initiatives of this talk is basically give you some idea of what we're thinking about at NRO in terms of time domain astronomy. I'm going to introduce things like the VLA Sky Survey, the current way to implement to get time domain astronomy on our facilities, as well as some commensal observing system, and then a interesting rapid response capability that is not put into place, but possibly something we're going to think about. So the first most important thing is the VLA Sky Survey. It was recommended after it was born out of this 2013 conference that we had, and basically is going to cover the entire sky at radio frequencies at between 2 and 4 gigahertz and 3 observing epochs. We are done with 2 observing epochs. We have just started our 3rd observing epoch, and I put a link here to a paper that describes the summary report from that conference that basically outlined the concept of the VLA Sky Survey for looking primarily for transients. I'm sorry about that last bullet point. I redid a slide. I recycled a slide. So Mark Lacey, who is the VLA project scientist, gave a talk recently on this to another group of people, and I just followed up with that. But as of today, we're starting the 3rd epoch of the VLA Sky Survey. All the data are available publicly without any proprietary time. It's all images, quick look images, as well as deeper images that can be accessed at any time. The primary way that we go through, they're not seeing the slides? I'm sharing the screen.
Maybe
stop sharing.
Yeah, we're trying to.
Oh, got it. Start. Should I do the PowerPoint? Or just...
Sure, you can do it.
Sorry, everyone. No? Can you see the slides now? Okay, let's try it one more time here.
Yeah.
See, let me get out of here for a minute. Do this. All right. All right, let's try it again.
Yeah, you don't worry, just produce it.
Okay. Okay. Sorry, folks. That's all right. All right. I don't know how much time I got left, so I'm just going to keep going. The primary way that people apply for target of opportunity or triggered time observations through our DDT process, the director's discretionary time. They're submitted through the proposal submission tool for NREO or the Green Bank Observatory and through the ALMA observing tool. I've just kind of compiled some numbers over the last several years. We've received about 364 DDTs, and about 184 of those were these target of opportunity proposals that need to be followed up. There's also a possibility to actually propose for time critical or time constrained observation. This is done through the regular proposal cycle. So during the process of the proposal submission, either in August 1st or on February 1st, you get the option of selecting either triggered or time monitoring proposals. I just want to point out that all these things right now are currently very passive. So it is up to the PI to let us know when you want to trigger your observation or you want your set your time range for time monitoring. Typical response times for all of our facilities at NREO, whether it's one of our North American facilities like the Green Bank Observatory or the VLA, or ALMA down in Chile, is could be from anywhere from minutes to hours. So we are responsive if the PI actually tells us to get on the telescope and to execute their program. So as we just heard about SWIFT, we do have these time critical programs, especially with joint observing programs with SWIFT and other facilities that are very high in the queue and could interrupt observing programs if something comes up like that. So we do have these options available. GBT time domain astronomy, pulsar timing is the primarily thing that we do on the GBT, as well as nanograv in order to look for these the timing of pulsars to look for gravitational waves. And we also are now installing an ultra-wideband receiver that goes from 0.7 to 4 gigahertz. That's going to be used primarily for pulsar timing, but could also be used for time domain astronomy and will be pretty much available the entire time. So the problem, though, with the GBT rapid response, if you want a particular instrument on the GBT, it may be difficult to actually find that particular instrument at a particular time of the year, given the weather and everything going on in West Virginia. So we can't really guarantee a particular instrument for a project, but except for this wideband receiver, that should be up all the time for the investigating time domain objects. Now, I'm going to talk a little bit about our commensal observing systems that we already have bolted on to a couple of our facilities. For fast transients, we offer something called the Real Fast system. There's a link there for you if you'd like to look at that. I'm going to talk about that over the next couple of slides. This is attached to the VLA. It's observing all the time, even especially during the VLA Sky Survey. And the VLBA, the Very Long Baseline Array, which is across the entire continental United States, Puerto Rico, and Hawaii, is a commensal fast transient system that's dedicated called VFaster. And so that I gave a link to the paper that describes the VFaster instrument as well. And then we also always, we have this rapid response capability through our resident shared risk observing on both the VLA and the VLBA, where you can go and help commission additional capabilities. So real fast, oh, that went real fast, didn't it? Let's try it again. Real fast. It's attached to the VLA. It's attached to each of the, it's attached to the antennas that is collecting these data. It goes through this 64 GPU cluster for real-time imaging and transient detection. So what we offer for the VLA is not only just the detection of the event, but also a very accurate location on the sky. And this is really what you want to, this is really what you need if you want to identify these, the location of these transients. I also highlighted a paper there if you want a more complete description of the system. Give you an idea of our field of view for some of these things. If you look at the field of view of Parkes and the Green Bank Telescope, Arecibo and the VLA, and depending on the array configuration, just how fine detail and just how far we can get down to the resolution in order to really locate these objects in the sky. And it's been in operation now for several years. We have a VLA detection of a fast radio burst. Here's the initial detection of that object, and you can see it was kind of offset in the telescope beam, but we actually detected the object and then localized it with its position in the sky. So you can see the de-dispersed time series at the top and how it decayed, and then the location of the object. For fast radio bursts on the GBT, this has been done over the last several years, and the question is, why are some fast radio bursts polarized, and where does this polarization fraction depend on frequency? And so they have started looking at new models for depolarization due to scattering. So this is a reference here, and the detection of a fast radio burst on the GBT. It's kind of annoying me. Supports some arguments that these fast radio bursts live in very complex environments. Are they part of a supernova remnant near a black hole or in a pulsar wind nebula? And the detection of one of these fast radio bursts on the GBT, it not only, we know that it's what changes in the rotation measure, but in this particular case, this fast radio burst actually changed sign of the rotation measure as well. When I was given these slides from our experts out in Green Bank, I actually asked them, okay, for these blue points that you see on the slide, did I do something wrong in terms of the aspect ratio of my slide? They're like, no, that's really where they were. So the GBT measurements for these fast radio bursts are actually in those locations on that particular graph. So one was taken very early on, several years ago, and then the one more recently shows this changing rotation measure, but also the sign of the rotation measure. So this is an interesting part of science that we're still trying to investigate what's going on. What you would really like to know is have an interrupt. I think that's what we're talking about here, is if something interesting goes off, you interrupt whatever's going on, and then we get on that very interesting object very quickly. So this is just a flow chart of how we would introduce this kind of interrupt into our system. The problem right now is, given our current system and as we start transitioning to hopefully NGVLA construction, we don't want to do a lot of initial edits to our existing observing software. But it's something that we consider for NGVLA operations, is to put an automatic interrupt into the system. So if something, you get an alert on your phone, it alerts an array operator, and they could go right on onto that source. An interesting idea that was brought up in Green Bank recently is the GBO 20-meter telescope. It is a primarily educational telescope. It operates at low frequencies, primarily at L band and X band. But it is very undersubscribed, and we have started discussions of putting in a automatic response system onto the GBO 20-meter if it is, if you think that it'll be useful for the type of science that you're interested in. So this could be done, I kind of give you a little bit of the details of the 20-meter telescope, but it is a possibility if something interesting is observed with the 20-meter, then we could follow up on that GBT or the VLA. So it's a possibility, and we're really looking for feedback from the community if we want to pursue this type of produce this type of observing system on that telescope. So just give a quick where we are with our transient science. The VLAS program will be completed over the next several years. It's available, publicly available. Anyone can use it. It's images and spectra. The DDT Trivic program is healthy. If I got 4 DDTs proposals submitted a day, they would probably overload the system. So we are not as good as Swift in this case. We get about 4 DDT proposals for transients and things every month. So we are thinking about that. RealFast is up and running on the majority of VLA observations, including VLAS, and this establishing a general rapid response capability where we interrupt programs is not really considered feasible at this time, except for possibly the GBO 20-meter or for NGVLA operations going forward. So I just want to leave up my summary slide and say thank you for inviting me. And again, it was really something to think about, especially when we start seeing those numbers from Swift, where if we handled 1,700 triggers and observing a day, we would probably choke the entire system. So we are starting to think about this. And we really want to work with the community, for example, setting up just something blanket on the VLA or on the VLBA from input from the community that is just run when something goes off, putting together a simple web form like Swift has as well to just trigger this scheduling bot to go off. And then, hopefully we'll be prepared when Ruben comes online in order to follow up some of these transients. So thank you very much for your time.
Okay, so
Yes.
Tony, thanks a lot. The question I had is regarding, before we go to the nominal survey, there's going to be this data preview 1 and 2, smaller chunks of the sky. So that would be a really useful exercise to see how many transients and how we can deal with it. So do you foresee that that type of process will go through, like we can ask for peer review time and then standard peer review proposal in the standard way for VLA?
Yeah, I think we have to rethink how we're going to do this,
Okay.
right? I mean, and this being invited here and start talking about, this time domain science in a different kind of way. So setting up through the regular proposal review process, just a blanket, if a triggered program goes off, that we get on the VLA very quickly, is something that is what we do right now, and we could execute that program. Something where really something interesting goes off that's not proposed for, but we need an interrupt of the system, we have to start thinking about how to do that. Because right now, it is possible, but it's very passive. We are waiting for you to tell us what to do instead of getting on the object very quickly. So if we could work together on possibly doing maybe not completely active and robotic, but not completely passive waiting, somewhere in between, I think we should start talking about that, working together. This AON program, for example, is very interesting to me. I haven't heard about it before, but getting into that network would probably something that we could do and think about in joining.
Thank you.
Yep.
Sorry for the technical hiccups here. So we will not have time for any discussion, but I'm gonna... Sorry, I can't get out of here. I'm gonna bring up just one last slide that we had put up of the questions we wanted to discuss, and maybe if we can take those on Slack and on the unconference sessions on spectroscopic follow-up, there's one. That would be great. So, oh, and they're not showing. Anyway, I think we can end it here. We're late. Okay, thank you, everyone.